This is the third video in the sequence, and it continues from the previous one, looking at the stress concentrations in a flat steel bar subject to bending moment and axial force. So the previous video looked at the effect of bending moment. This looks at the axial stresses, the stress concentrations, and looks at how to probe and to analyze the stress output in some more detail along different paths, to adjust the contours and things like that. So when we had finished the analysis, and we come back to the workbench main window, we see that all the options are ticked green, so they're all finished, so they're all fine. We can go back in by double clicking on model, and that as it says, starts the mechanical module. It's a good idea to save your project every now and then when you're happy with the results. Or maybe save different versions so that you can always go back to a recent version if you mess things up. So in mechanical, this is what it looks like. This is what we analysed. An applied moment there, a support at this end, and looked at things like normal stress and the stress contours, okay, and the stress concentrations around the hull. So now we look at axial tension. So we will right click on the moment load and suppress it, so that switches it off. Right click on the axial force that I defined in the previous video and unsuppress that. So as we see here, it's 560 kilonewtons acting in tension. Now it has to reanalyze that, so we have to get the results, we need to click solve, and that takes a few minutes or a few seconds. And now the analysis is finished and everything has a green tick, so we can look at normal stress and look at it that way. So the load is designed to produce an average stress or nominal stress in the bar of 100 newtons per square millimeter. Now we can probe that, click on probe and pick some area here, so that's 100, that's 100, that's fine, and out near this. Okay, so we need to then look at what's happening around the hole and around the notches. Okay, so let's zoom in on the plus arrow here to zoom in to look at that and rotate it maybe just to see. Okay, so axial tension, some very high stresses in here, well, the maximum is 826, so it's around here. Over here is 100, but it peaks here at, well, somewhere, it peaks somewhere here, I guess, but the main maximum is occurs here, as it says. So, and there's some variation across. So this is quite a thick plate. You know, the theory is based on thin plates, so there is some kind of three-dimensional effect going on there. If we look in here, we see that there's some compression in these zones here and here. So that there's some negative stresses. If we probe those, we see there's some negative stresses here. So there, it's positive, negative there and there. So it's quite complex behavior going on there. Now it's useful to try and understand what's happening in this part of the region. If we look at that's the undeformed shape, but if we exaggerate or that's perhaps slightly exaggerated, or significantly exaggerated, but what it highlights is the fact that these parts, while the bar is in tension, these parts are going into bending. Okay, so there's extra tension here and compression here, reducing. There's a slight reduction there, but a very significant increase in that. So the theory gives us that when we introduce a hole like this, removes a lot of the material. So the nominal stress based on in this region, which is the stress due to the just simply due to the reduced area of material. The nominal stress according to theory is about 390. Okay, and that's where we're getting those kind of numbers from. Okay, but the on top of that, there's a stress concentration factor of about 2.2 according to the theory, which brings it up to about 850, and we're getting 826 there. So it's reasonably accurate. Well, it agrees reasonably well with the theory. Okay, the stress concentration factor of 2.2 is slightly approximate. It might be 2.15 or whatever. So it's, but so it's close enough. We can also look at the notch if we zoom in on that and see what's happening. This is in axial again. So we can see that there is a, and probe that, we can see quite more than twice the nominal stress. At the edges of the notch, maybe not surprisingly, there's practically zero stress because there's no material on the other side of the notch, if you like, or in the notch to provide any resistance to the tension there. Okay, now we can just play with the contours a little bit. There's various things you can do with the contours. You can move them around. That's easy enough. But you can also, if you click on any of these, you can add. There's click there. The plus button appears. You can add in more contours up to some limit. You can reduce them again. So that gives a little bit more detail in areas that are significantly away from the maximum values. It's the max min over the whole structure that determine these contours. So you can do various things with that. You can double click on these and you can change the numbers. You can manually set the interval. So say if I want some detail around between 180 and 200, well, maybe between 200 and 240. So I could change this one to 200, this one to 210 maybe, this one to 220, this one to 230, this one to 240. And as you see in this area here, if we zoom in, we're getting more detail of the variation in stress around between the 200 and the 240. We can right click on the contours and there's a logarithmic scale, different number of digits, the color scheme. We can reset it and it'll go back to the default. Okay, so that can be useful. We can also point out that there are some end effects. So if I zoom in on that end of it, we can see there are some stress concentrations, or apparent stress concentrations there. You need to be very careful when you're in finite element analysis near supports. There may be stress concentrations which may or may not reflect the reality. The model here says that this surface is entirely fixed. So there are these stresses appearing in the corner. They may or may not be correct. And the meshing is not particularly, if I show the elements there, the meshing is somewhat, fairly coarse there because I wasn't that interested in it. But so you just need to be careful. The mesh here, of course, is as we know, much more refined. Oops. And we can have reasonable, more confidence, let's say, in the results there. To, as we saw in the last, to delete the probes, we click up on this icon that says up in the top left-hand corner that says label, and we should be able to click those. Sometimes the probe, it doesn't really matter whether the probe is on or off. Sometimes it seems to. Okay, if you switch it on, we have to switch it off. So sometimes it's a bit unpredictable there, but you can experiment with that a bit if you get stuck. But basically, to delete probes, you go up to that label. Another idea, you can smooth the contours to give as the name suggests, kind of a smoother, perhaps more realistic view of the stresses. So we get that. Our contour bands are sharper, kind of more definite. Alright, so the other thing I wanted to show in this video is how to look at variation of stress along different paths along different lines, maybe along the top edge of the around the notch, maybe around the hole, across this section here, across maybe this section here. Okay, so those kind of, so to do that we use what are called paths. There is another way which you can section. Now let me see, there are up here there is an icon called section plane. So if I click on that, new section plane, down here in the bottom left hand corner we have some icons to manage these, and we can basically take a cut down through, say there, and it does that. Okay, and we can zoom in and look at that in more detail, what's happening through that. Okay, so it can be quite useful. All right, now if we go down here we can just turn off that, you see the tick there, section plane 1, we can just untick it and it goes back to the full structure. Okay, so just switch it on and off. Now possibly a more useful way to do it is to introduce, or to have a more detailed look, is to introduce these ideas of paths. Okay, now to do that you need to go all the way up to the model, right click on the model and insert what's called a construction geometry, and then under construction geometry insert a path. Now the path can be between 2 points or along an edge. Now some of them might be useful to do it along an edge, so let's do that initially, and we need then to go up to select edge up here and maybe select that edge around the outside of the hole and apply that geometry selection. Okay, so we have a path defined there. We can rename it around so let's insert another path again along an edge, and I'm going to do it along the top edge. Now I'm going to come down around the notch, so we need to just control click and do that and that. So there's 3 edges there, and apply that, and it says 3 edges, and we see that. Now it has, in that particular one, it has the start of the path down this end at the right hand end. Now because we're going to be looking at it, well, we can right click on path and flip the path orientation, and that says it starts here at the left and goes there to the right. So that makes more sense in the output. So that is we can just hit F2 to rename it top edge. Now I want to do some sections through it, so I want to do a new path. Insert path here, and I'm going to use 2 points in the global coordinate system, and I think this is probably the most convenient way to do it, is just type in, now I know that this is for the notch, -300 plus 64 is the, well, maybe -64, that is the first point, and then -300 and the y coordinate plus 64, because the depth between the notches is 128. Okay, so there's a path there, and between notches, and one more then over here at the top of the, so let's again construction geometry. As usual, when you click on construction geometry the toolbar changes, and there is a construction, you can just click path there, and 2 points. This time I wanted at 200. 52 is the base, the bottom of the hole. The hole is 52 millimeters in diameter. 270 is the top. Oops, 70. Okay, so that looks good, and we'll rename that to now, just putting in a path doesn't actually generate any results, so we need to go down to the solution, insert stress, so we'll look for the normal stress in the X direction, and this time the scoping method, you click on that, you pick path, okay, and then it says, well, which path? So I'm going to do that on all of them, okay, so insert stress, normal stress, and you have to do it one by one. Top edge, stress, normal, and between notches, all X in the X direction, normal stress is in the X direction, and one more, normal stress, path, the top of the hole. Okay, so quite a useful feature then, if we just do shift and click on normal stress 5 there, just give them the normal, and shift and click to there, and right click on that and rename based on definition. We'll see what it does. It puts in the name of the path in the time thing. It is slightly more for more advanced analysis where you're applying loads over time, but here it's just one time step, the load is applied. At the end of the time step, it's the full stress. Okay, so that's ready to run now. All these lightning strikes mean that they need to be so if we it should come up, evaluate all results. Okay, maybe I have to click on the solution. Okay, yeah. When I right click there on any of them, I think, in fact, on the solution, evaluate all results. So it doesn't go back and solve it again. It just picks up the results, the new results for these paths from the output file. Okay. Okay, so let's pick along the top edge. That's probably the easiest to think about. So it's showing the stresses along the top, along this path, and down at the bottom here, it's showing a graph. Okay, so the average, the nominal stress is 100. So in regions away from the stress concentrations, you have 100 newtons per square millimeter. As you come into the notch, at the edge of the notch, the stress drops to effectively 0. Then it peaks down at the bottom of the notch, up around 200, as we've seen. Back down to 0 up at the edge of the notch, then along 100. And then it climbs up to there's nominal stress, and that's the nominal stress due to the reduction in material, around 380, 390. And then so at the center of the top edge, it reduces again and again peaks again and goes back down. Okay, so around the hole, that shows you where and you have to imagine this going around in a circle, and this is always the X. It's the stress in the X direction. Between the notches, that's like a bending stress diagram across, or sorry, not bending stress, axial stress. Again, it's 100 in most of the region, but then it picks up as it approaches the notch and goes up to 220. So there's a stress concentration of 2.2 or so there. And at the top of the hole, you get this kind of a bending stress across it, which you saw in the deformed shape, where this is a classic bending. Now it is horizontal. You can do various things with this graph. You can, if you click on this one, it says auto hide. It disappears up here to the top right hand corner. If I click on graph, I get that. Okay, which is again a classic bending stress going from around 100 all the way up to 767. That's on the outer surface, so the maximum actually occurs deep in the center of the bar, but this is at the outer surface, so it's not quite as high as some of the maxima we saw earlier. So if we click away from that, it disappears. If we click on that, we can undo that, click on the pin again, and it comes back down here. This tabular data, so we can click some point somewhere 7.5 millimeters in, so that tells you that, and it'll highlight here what the value is. We can click there, copy, select all, just do Control C in fact, and go into Excel and paste, and we get the results there, and we can draw whatever graphs we want. You can also do an image copy, so if you want, say, a copy of that picture, you should be able to go up here, copy the image to the clipboard, so that's Control C. Possibly, and then if I do that, what happens? Yeah, so that diagram, that gets copied in there into Word or Excel or whatever report you want to do. Okay, so that's a useful feature. Yeah. So finally, let's just reactivate the bending moment and have a quick look at the stresses along those paths under bending. So I'm going to suppress the axial force, unsuppress the bending moment, and click solve. So it takes a few seconds, so I'll skip, and it has finished. So if we now look at the bending stress along the top edge, okay, so the nominal bending stress is 114. That's in the unstressed region, or away from stress concentrations. As we approach the notch, it drops to 0 just at the top edge of the notch, and then increases to 246 at the base of the notch, then back in the normal zone. And again, it increases. Okay, they're negative stresses because they're compression, so it increases to, if we click on that, we see over here, to about 193, and then we click here. Again, it drops to about back to about 100, just above the notch there, above the hole. Right. So between the notches, we get this classic, as you'd expect, bending stress distribution, but with a kick up at either end. As it approaches the notch, there's a fairly standard bending stress distribution here through most of the bar, but as it approaches the notch, there's a very sudden increase in stress there. And if we look at that, this is it's here, it's at the, so it's along this path. We'll turn off those maximum in. So this is the axial stress, sigma x, along this, under an applied bending moment. Okay, so we need to interpret that. So yeah, it's a maximum at the start, isn't that what we're saying? If we look at normal stress and probe that, yeah, so there's a peak there, compression there, because this is in the compression zone, but additional compression there. All right. And so we're looking at that. So it's dropping from compression of 264 to this. Okay. So lots of ways of looking at output. And click on that, and we should get that. So once again, let's just finally look at the let's exaggerate the and try and see, can we see what's happening around the hole. Okay, so it's bending up like that, I guess. So it's increasing the compression there. This seems to be bending in a bit. Does it? Hard to say, really. Hard to say because of the curved nature of the shape, but fairly complex behavior leading to significant stress concentrations. Okay, so that concludes that video and shows you how to interrogate the results in more detail with different techniques like paths and section planes and things like that.